Yeah, they are clear.
Okay. Okay. Fine. Again, so good afternoon, all. So, welcome to Machine Learning for Material Sciences. So, we have been covering a bunch of ML for a while now, specifically neural networks. And so, just to give a very quick recap, so again, neural networks started from biological inspiration of neurons, how they fire. They either fire or don't fire. So, in artificial neuron, when we come back, they either activate or don't activate. Activate means they pass the information. They not activate, basically they don't pass the information. That is zero. Okay? And we specifically looked at a single perceptron, which basically equivalents of like a single neuron, and then we connected them together to create a multi-layer perceptron. Yes, and we also established that give universal approximation theorem applies, and this is specifically where you have input layer, one hidden layer, and output layer, and if the input layer can have some number of like hidden neurons, yes, with and the notion is basically like how many number of neurons you can have based on that approximation, but it can approximate any function. And then we looked at other variations also, like for example, in neural network, we looked at how to optimize, for example, backpropagation we studied, chain rule and everything. That was lecture number 2. And lecture number 3, we looked at, yes. So in lecture number 3, we looked at the gradient descent family itself, stochastic, batch, and the mini. And then we looked at the momentum, and then accelerator, like Nesterov's accelerated gradient. Uh, then we looked at how you can have not learning rate for everybody, rather adaptive learning rates, like Adagrad was there. Then we came to Adam. Adam had both momentum as well as Adagrad, basically per parameter learning rate. How that was really nice. So everybody uses Adam now. And then we looked at again vanishing gradient problem, exploding gradient problem, then the bias variance trade-off. We looked at the regularization techniques, the L1 and L2. And then we looked at specifically a dropout, which is a very specific to, let's say, neural networks, where we randomly drop. I will show you the figure probably. I'll come back. Then we looked at weight initialization strategies, right? So one, so exploding gradient and specifically exploding gradient. One of the solutions that was proposed was basically doing better initialization. So that better initialization can be, there are few methods to do so. One of them is Xavier or Glorot. So they basically say uniform or Xavier. These are normal distributions only having different mean and variance. And the other one is, and those are specifically applicable to, let's say, tanh and sigmoid. If you have ReLU, then there is a timing here initialization. Yes, that is also normal distribution, but that removes the I hope you remember, like 2 over n in and n out, and it specifically removes the n out, so it remains 2 over n in. That is specifically done because in ReLU, everything that is negative, it's basically zero, so it basically drops half of it. And then we discuss some other stuff like learning rate scheduling, like adaptive learning rate, step decay, exponential decay, cosine annealing, and learning rate warm up. Right? And we discussed for everything why this was important. And finally, we land up with like batch normalization. Right? So instead of finding, oh, I hope you remember like why we need normalization, because features eventually they don't have relation with each other. Some features can be very high, some features can be very low. So that's why we do normalization. But instead of doing normalization across the entire batch, which could be computationally expensive, you can do it within the batch, right? There are some goodness about it. Goodness is basically it creates some kind of noise that helps in generalization. There is no bad per se, but the bad is like basically you can end up with calculating mean and variance of a really bad batch. Yes. And so that's what we discussed in 3, and in 4 we, yeah, so 4 I think we already gave a start. It did contain similar notions that we had covered, but a little bit further into the how do I say, uh, into the same depth that we had earlier. So we looked at residual connections. Okay. My bad. I had pictures. I don't know where did they go, but anyway. Let me see if I can drag this. Hmm. Okay, I'm not able to grab pictures, but regardless, yeah. So fine. So at least we went through the first question we asked last class, like, is it better to go depth or width? Width meaning adding more neurons to the particular layer, or depth as in adding more and more layers. So we basically argued that more depth provides more efficient approximation. Yes. And it also provides a little bit more of hierarchical learning. Yes. Uh, sorry. And oh, nice. So pictures are here. So input layer, hidden layer, and output layer. And uh, then we came to vanishing gradient and how the maths works. Why does it become actually vanishing? Like, why does it vanish? Why does it goes closer to zero? And how do some like approaches basically help it? Like one of them was dense network and highway network. There's all a skip connections. And sorry. Dense and highway networks, these are skip connections. And skip connections are basically if you go from like the input, let's say X, and there is an activation, let's say happened, and then layer 2, and then you add. But instead of information just flowing from X, then layer 1 and layer 2, and so on, there might happen a chance that the information that was present in the input might have got lost because of all this activation layers and multiple layers that it passed through the information. So what you do is you pull the input from the input itself and add it to the output, let's say output of any of the layers. It need not be direct output. So that is basically a skip connection. You are basically skipping all the internal connections and directly jumping forward. Yes. You could do this in two ways, like dense and highway. And specifically, we looked at also, I told you about residual connections. Uh, it's almost similar, but residual connections are same. They just do it a little bit different way. Anyways, we'll have a look in the next class. And the next one is dropout. I told you specifically dropout is, I hope you remember this diagram. So this one was basically you have an entire neural network. Every time you train for every mini batch, you basically drop random set of nodes. Yes. And once you drop this one, this helps you generalize because every time you are learning a new neural network, because the next time these will not, this may not be the nodes that you are dropping. Rather, this could be another set of nodes that you're dropping. Yes. So that becomes eventually a new network. And while testing, we make sure that entire network gets used. Yes. And we looked at a little bit more mathematically how dropout looks like. We looked at what you can actually drop out. So for example, you could drop the nodes, you could drop the edges, or for example, in CNN, you could do a special dropout. We'll take a look as we come, but at least standard dropout and drop connect. So standard is basically where we drop neurons, and drop connect would be instead of neurons, we drop the connections, or let's say the edges or the weights itself. Yeah. That means information comes, but information from that node does not come to the next node if you drop the edge. Yeah. Fine. And I stopped here, basically early stopping. Yeah. Okay. Are there any specific questions before we move on? Just to make sure. Okay. If you have any questions, please type on chat. I will cover if you have any questions. Fine. So the next part is early stopping. Early stopping basically says, like, let's say you have this validation loss um, at every epoch, let's say you calculate. I hope you remember there is a training loss, and there is a validation loss, and there is a testing loss. Training loss we do to find the parameters of the model, let's say W and all that stuff. Validation is done to verify if your training was actually correct before moving on to testing. Yes. But also validation loss is also used to find out your hyperparameters. Yes. So technically what you do, you train and you validate at the same time. Yes. So you have, for every training after a initial weight update, you calculate validation loss at that point. Yes. So if y is equal to mx plus b, given a particular value of m and b that you have learned based on few mini batches or one mini batch, let's say, the moment weight gets updated, like m and b gets updated, you run the same model with M fixed and B fixed on the validation set, and you find out validation loss. Yes. So, and you basically keep on tracking. Yes. So that L val T is basically the validation loss at epoch particular T. Yes. That could be epoch, that could be batch also, or could be iterations basically. And what we say is basically you just stop the moment. Sorry, yeah. And you stop the moment the validation loss basically increases. Yes, for few consecutive epochs. Yes. Uh, you are training loss reduces. You are also validating at the same time, validation loss also reduces, right? But the moment validation loss increases, that means you are training, but your training is now overfitting to the training examples that you have. That means it's memorizing the training examples. So it's not looking at validation to give an exam, rather it's memorizing everything that is training. The moment the validation does not match with training, it will start giving you an error if the model does not generalize, right? So that's the idea behind stopping whenever the validation loss becomes greater than what it was before after k many epochs. Yes. And here k is also known as the patience parameter. If you want to know, like this much amount of patience you need to have before actually updating, because there is a chance that validation loss will keep on increasing. If you have, I hope all of you have tried training models. The moment you try training models, if you see, the loss will keep on, like, fluctuating. Validation loss will also keep on doing so. But if it continuously increases, let's say for k number of steps, then we have an issue. And so what is the, like, mathematical justification for this? So basically we are trying to find out the optimal bias variance trade-off, right? So as training will continue, the training loss keeps decreasing, but the validation loss eventually will start increasing due to overfitting. Yes. So we want to basically find this T star, like at the iteration time or the epoch time or whatever you're tracking to. So the optimal stopping time that minimizes the expected training test error, because we don't know the test, so we cannot say, okay, this will reduce, but expected test error. So we cannot directly compute this because we don't know the true test distribution. So, however, through validation, we are giving a hypothesis that, okay, if we have good validation loss, we'll eventually have good test loss as well. Yes. So it's like a proxy. Yeah. And the typical patience values can be like 10 to 20 epochs, if that makes sense. And otherwise, if you go through it, there is still fluctuations. And never make it k is equal to 1, there will be fluctuations and you will lose further training optimizations. Fine. And so what is early stopping in the whole? So it's also kind of like, how do I say, like, it stops the model from overfitting, right? So overfitting, one of the ways was dropout. So here we are basically reducing the complexity of the model. And another way to do, like, stop overfitting is early stopping, right? So I think I told you about this before, but this is one of the techniques we use to stop overfitting. The next is data augmentation. Okay. Uh, Now, data augmentation basically says is it's basically a mathematical transformation, some form of transformation to training data to either if increase the effective size of the data set, right, and make models more robust. So I think some of the rules are basically if you have very small data set, right? If you train a very large model, either it will not train at all, and if you have a very small data set, technically you will end up remembering everything. Yes. To do this, we rather do something called data augmentation, where typically we are basically for each sample, for let's say each sample, we create multiple other samples. Yes. So we're trying to increase the amount of data set that we have. Yes. Specifically, you can take a look, like for example, pictures. One of the ways to do data combination in pictures, if you like tilt it a bit, right? So you can have a picture like a dog. It's like, let's say you like you have a face of a dog as a picture. Then you tilt it a bit, or you squeeze it a bit, or you skew it a bit, or you increase the contrast a bit. Yes. Or you can crop it a bit, crop and then scale. Yes. All these are like things that you can do with the image itself. And similarly, same things apply to all other numerical values and categorical values also. There are different sets of augmentation that you can do. Few examples are given here, but I hope why augmentation is necessary, I hope you understand. We have few data sets. We want to increase the number of data sets so that the quality also increases and also the model's capacity also increases. For example, if a dog is only looking at straight and all those examples you have, then what if the dog looks a little bit sideways? Do you still have the, like, is the model good enough to capture those kind of, like, tell that picture is of a dog? So to increase that capacity also, all these approaches are done. Yes. So for example, geometric transformation, we have rotation. We can do translation by adding a vector t. We can do scaling by multiplication of factor. Yes. And statistical transformations also there. You can add Gaussian noise with mean zero and variance. Yes. And then otherwise, you can also have normalization being done. Yes. Theoretical foundation, basically, what does it say? It says augmentation increases the effective data size, thereby reducing overfitting. Yes, by making the model invariant to transformations. Fine. So we have looked at three methods now till now that stop overfitting. One of them is dropout. The second one was always stopping. Then there is data augmentation. Fine. Now, these are few other loss functions. I'm not saying that you have to, actually you have to remember this. These are very few. So specifically for regression, I think we have covered like mean squared error and all this stuff. I will come back to again those. But for classification, we have looked at cross entropy in some portion, but we have looked at specifically at likelihood. Yes, specifically logistic regression, we have looked at it in detail. And we don't do likelihood, rather we do log likelihood because it's sum, there is no exponential, it's easy to calculate and all. And then there is cross entropy loss. Yes, cross entropy loss is basically a generalized log likelihood. Yes, and you can have its derivative that is given. Yes, and cross entropy is basically is the negative log likelihood which we want to minimize. It's exactly the same, and the derivative is as given. And this is useful, specifically this particular derivative in the backpropagation, right? So if you remember, like during backpropagation, we calculate derivative of dl with respect to, let's say, dw1, right? Then we do a chain propagation. But first we have to calculate. There we have to calculate with the respect to loss, there has to be a derivative. And if the loss itself is like a cross entropy, then this is the derivative that gets calculated. Fine. And then what do you do for if, because, okay, so cross entropy specifically, it's like more of a binary class. If you look at this, like what if you have like a multiple class cross entropy? That basically goes back to a softmax function, right? So for every class, we can have e to the power like k maybe and divided by summation of all of those. Yes. And it is differentiable everywhere, and then the multi-class cross entropy will look like this: yk log pk, where pk comes from e to the power zk by summation over e to the power zk for all the classes. Yes. And its derivative also is simple, it's pk minus yk, which is important for us. Yes. And that's why, like softmax function, you will look at every paper that you will read, these will come up like cross entropy and softmax. This will keep on coming up. But I hope your background and these classes will help you. Okay, this is it. Why do we use it? Fine. The moment multi-class comes, you make sure this is multi-class cross entropy is getting used, not just the cross entropy loss. Otherwise, it will give you a dimension error. Now, loss functions for regression. We have MSC. I hope you remember that. The mean square error. Uh, the only problem is it is very sensitive to outliers. If something is super far away from the actual, it gets squared, right? And what if that super far away from actual is actually a noise item? Yes. Then it creates, then like the model believes that that is the only loss that I have to reduce, right? There is another loss function also like mean absolute error MAE. So this is just simple. We just calculate absolute, but the only problem is it's non-differentiable at zero, but it's robust to outliers. Some robustness. There is no square term, so the outlier does not have compounding effect. Hmm. There is also Huber loss. So just yeah, and this basically gives like both like the best of both worlds. It's quadratic when the error is small and less than delta. So there will be smooth gradients there. So whenever the error is small, you will have error is quadratic, and so you can have nice derivatives around. And it's linear when the error is too large, right? So it basically does some kind of compromise, taking best of both MSC and MA. Hmm. And equation here, delta will be the hyperparameter that you would have. Yes, so smaller the data delta, it will make it more robust, but then less smooth. Larger data will make it smooth, but it will make it less robust. Yes, fine. And now multitask learning. Will fine. Okay. We'll come back to multitask learning in 1 minute. So I'll cover this one first. So okay, advanced regularization. So yeah. So remember, like we had regulation terms involved. So L1, L2, dropout. Yes. So all these we had. Now there is something else called a spectral normalization. It's basically an advanced technique that controls Lipschitz constant of your network. Basically, we decompose the weight matrix into singular value decomposition, and then W will be equal to like U sigma V transpose. And the spectral norm is the largest singular value, yes, which is the maximum norm of W times H over all unit vectors H, right? The spectral normalization will divide W by its spectral norm, giving us WSN. Hmm. And this basically will constrain the weight matrix to have a spectral norm exactly as one. Yes. This effect will do, what it will do is basically it will constrain the Lipschitz constant of L of the network. And Lipschitz constant measures how much the function output can change relative to the input change, right? It just controls the variance. Now the constraint variance of the function, I hope you remember the Bayesian variance, that same variance. Now the constraint says the norm of f of x1 minus of f of x2 is at most L times the norm of x1 minus s2. Yes. So that's basically the constraint we have. And then this is specifically useful to make sure that we do not make any changes, or we do not basically overfit the function, which basically causes a lot of variance, right? Because the neural networks itself come without any bias, so you can actually train them to be have very high variance. So this particular constraint will help us basically making us the training can be more stable. Specifically, these are used in GANs, if you don't know, generative adversarial networks, but that's not the point. Neural networks in general can also have more stability, and it specifically says that variance of the function will be under control. Yeah. Now, the next thing that I wanted to tell is basically layer normalization. So you remember the batch normalization that we did a little bit earlier, last class. And what we do here is basically we normalize across batch dimension, right? So if you have take mini batches of the data set, instead of doing normalization across the entire data set, we do it over the small mini batches, right? The other what we can do is something called a layer normalization. Right, fine. This does across feature dimension. So how do I say this? So instead of doing batch normalization that takes all the features into account, uh, what you can do is you can normalize across the feature dimension itself. For example, you can compute mean and variance across all the features. Yes. So for example, if you see mu L and mu sigma, that is across, like these are computed with 1 over h times and then sum of overall of h features. Yes. Now, why should we use layer normalization instead of batch normalization? Two advantages. First is basically our normalization that we earlier calculated. I think I told like few minutes ago. It will depend on the mini batch that you have. What if you have a bad batch? What if you have a great batch, right? So all this great batch is fine, but what if you have a bad batch, right? Then the mean and variance will be very off because the data set are not in sync with each other, maybe. Yeah. So to avoid that, there is will be no batch dependency in layer normalization. Yes, it will work better with batch size one. Yes, and this is important specifically for when you are inferencing. So whenever you are basically trying to predict, while training you have a bunch of data, while testing you will also have a bunch of data, and validation you also have a bunch of data. But let's say now the model is trained, you told okay it can perform really good accuracy. Now you want to try it on your, let's say, paper. Yes, your own work. Let's say this is the material that you have found out, I want to predict its properties. Yes, but that is just one example, right? And uh, batch norm can only calculate across batch, right? And layer norm can also work very nicely for batch norm one. So specifically in that case, it's used. And second, it's basically any sequential model, layer norm is very important. Yeah, so very important. I would rather say it's more favorable to do so because batch norm will require you to hold the sequence, right? Only if the sequence becomes length of 5, only then I will calculate batch norm. Here I don't have to. Doesn't matter what sequence you give me, I can calculate layer norm. Yes. So trade-off is batch norm will train faster, but layer norm will be more flexible. Yes. So batch norm, of course, will be faster because we're taking batch by batches. Layer norm as you come and you take. And typically the entire, I will not say entire, but the transformers, the large language models, the chat GPT that you hear, they all use layer normalization in one of the steps. And they don't do batch normalization. Hmm. Fine. Okay, so now this is advanced architecture. So I have put attention mechanism preview here, but I will show you the code probably next class a bit where you can, I'll have the graph is in that particular code where you can appreciate it more probably. But what attention basically says, just because it is there, so we'll discuss. So it basically says if I'm in a group, let's say, uh, I'm in a sequence or a group of items, uh, the and I have some amount of, let's say, value to give. Yes, but my value will depend on the sequence that I am part of, right? And specifically, I will receive inputs from all my neighbors, right? It also belongs key fine. For example, like I'm looking at you with red eyes. I went to doctor for my red eyes, right? So it depends. Like the red depends on the locality or the entire context or my neighbors that are present, right? I'm looking at you red eyes. Probably I'm angry. I went to doctor. Actually, I have disease and actual color of red, right? So it just says that. So my value is fixed initially, red, but it will depend on the neighbors that I have. So if my neighbors will give me some information that basically comes from the key, and the query's value is what I have. Query is basically I am again. I am the red is the query. Key will be all other my neighbors itself. Yes. But again, we will discuss it in the next class a little bit more with the diagram so that this comes this way. But again, I just want to complete this in the sense. So we looked at a little bit more depth in architecture so that when you read papers, you will understand what is missing and what is happening. So we have depth and shallow considerations. We argued depth is nice. Width, of course, it will be way better, but the point is overfitting is possible. Finding the exact number of parameters is difficult. It becomes too high. It's also expensive and all those stuff. So what do? You start with proven architectures. Whatever has been working, start with that. Let your algorithm run. Let the program run. Give it some information. Yes. So let it training loss let it reduce, validation let it reduce, test loss let it reduce. Yes. The other thing is basically you can do something called an architecture search. So there are algorithms that basically search for an architecture. So it finds how many number of neurons should be present in every layer, how many number of layers should be there, which kind of activation function you should use, all those hyperparameters that we have thought about in a neural network. How many hidden layers, how many neurons in each layer, what should be the connection, what is the activation. All these questions can be answered through architecture search. That is called neural architecture search. That's a different line of research altogether. Not important right now, but if anybody says, okay, we have done neural architecture search, that's what they have done. They have found out by running another algorithm, they're basically finding out how should my neural network look like. Is it easy? No, it's very difficult also to do that because where do you start from? Where do you end from? What is the scope? What is the range? Yes. Uh, One advantage is maybe your domain knowledge will help you answer these questions. But typically, suggestion is again, rule of thumb, we go back, you start with the proven architectures only. Yeah, fine. And okay. I think that is the end, but I will go back to now multitask learning. Fine. So multitask learning here is if you it's basically says that what if a model can perform many related tasks simultaneously, right? So for example, in materials, let's say it also does, let's say, finds the magnetic properties as well as, let's say, some other property, right? There are two different tasks for the, let's say, finding the band gap, yes? Eventually, it looks like one task, but maybe it's two different tasks, yes? Uh, then the architecture will have a shared representation. If you don't understand, it's okay. Like I'm just saying. So what we are saying that from the material we will take into a common space. Material is in space of where we understand where, let's say, chemistry or physics has defined it. But for computer to understand that, we will have to absorb that entire materials into a common space. That common space is shared. Yes. But then for every task that we have, we take one channel, each channel basically path from that common shared space, right? So that will be like eventually a multitask, and then for every task we calculate loss functions like losses, and depending on how much we care about, like if the magnetic property is more important than like band gap within certain range, like forgive if I'm saying something absolutely wrong, but then like if the magnetic property is very important to us rather than maintaining whatever the band gap, let's say, range, then we give it more weight, or yes, in the loss. So but materials is in the space of physics and chemistry are defined. For computer to understand that, we have to take a mathematical representation of that particular thing that can either be after few layers of neural networks, or that can be just our understanding also. But once it is there in the common space, from common space we take branches, right? And then we, for each of the branch, we ask a different set of question, right? So the only challenge here would be like how do we find this lambda, right? Like which task is important for us? What if all the tasks are important? Then probably this won't help, right? Just summation and then by that much. So this is again, but this is what multitask learning would be. And one of the examples, for example, if you have, I hope you have seen this LLMs that come for, let's say, law LLM, right? That means it is also multitask. That means first it has to make sure the language is correct, and the second task is basically whatever it is telling, it has to be correct based on the laws that we have in India, right? So it has two tasks. So language has to be correct and the laws it has to be correct. So based on what is important for us, if language being a little bit shaky but the law has to be absolutely correct, lambdas has to be assigned that way. Hmm, fine. And there is another thing is called multi-label classification. So here multi-label would be like if you have a picture, if you just say it is cat or dog, there is just a single label because you are giving just y is one for it, like cat or dog, yes, or nothing. Multi-label meaning you say that there is a cat and there is a dog, or there are 10 swans, one cat, one dog, and two human beings, yes, in the picture. So that will be like multi-label classification, yes. So here, what we have is basically one label per example in multi-class, yes. But classes can be many, like dog, cow, cat. These are many classes, more than one, let's say. But multi-label is you have multiple label per examples, right? So that means you can, in a single picture, there can be many. And for that, you have a specific like multi-label loss. It looks exactly similar, but like the labels are multiple, yes. And we calculate loss per label rather than per class. And we can have a threshold also that will tell, okay, if there is a particular dog or a cat or no. Yeah. Okay. So that completes this particular chapter. Uh, I will just show you a few quotes that I have. And then if time permits, we'll jump to the next one. But let me show you few figures that will help probably appreciate more maybe some of the things. Okay. Okay, I hope this is visible. Yeah. Don't worry about the font size of the code. So just worry about the figure. Hmm. I hope this is visible. Hmm. So what we have here is basically, I hope you remember the loss function. This is a from optimization training technique. Yes. So this is basically a 3D loss, right? So the minima is somewhere here on like the parameter one, parameter two. That's where those values basically make your loss function zero. Yes. And and if you look at the right and the right hand side, so basically the contour plot shows, and then you have the gradient field, right? So basically we move in the opposite direction of the gradient, right? And from the starting point, we try to move to the global. Yeah. So there can be like a local minima, there can be a global minima. So based on where it will move, that will depend on the gradient direction. Yes. And the next, yeah. So if you look at this, so we started here and then this is ended here. So, okay, this diagram is tricky. Okay, so this one, yeah. So if we had, okay, let me see. Yeah, okay. So here, if you look at this, this is batch gradient descent. Optimum is here. On the big red star is optimal, and the end is the green button and the start is the black thing, and then SGD is, or like any other line, blue line or green line or red line that you see connecting from the blue from the black to the green, that is the path that takes. Yeah? So if you have batch gradient descent, it moves like this path. If you have SGD, it moves this way. If you have mini batch SGD, it moves this way. Right? Batch tries to move out of this, but eventually it struggles. It cannot move out of that local minima. To help that, what you can have is basically the momentum. So here, if you apply momentum, in batch it might not help. Let's say there is no momentum as such, but if you apply some classical momentum, then it starts moving. So because it allows it to basically carry forward the gradient, right? So it basically starts moving. And if you have Nesterov's accelerated momentum, it basically goes a little bit ahead, right? Look ahead. That means it instead of finding the gradient at that particular place, it moves a little bit ahead. That means it subtracts the current weight that we have, right? So it current gradient matters even less, right? So Nestor's momentum, you can see if we apply that accelerated momentum, then it actually reaches the optimum, right? So what I wanted to tell you from this figures is basically momentum works. Please use it, yes. And even if it helps with training and all that stuff. And this one is basically momentum figure, the loss convergence that I told. So loss is basically, and loss has to reduce. Yeah. If you look at gradient descent, it also stays silent. If you look at momentum, it goes this way. If you have an atom, this also stays silent. Yes. And there are days where atom will work, there are days where momentum will work. So this particular example, if you run it again, it will go either way also. Now, this is the thing where vanishing gradients. Vanishing gradient is basically where I told you like the output gets suppressed because sigmoid is there. Sigmoid, that if more than high, it will get suppressed to 1. If it is less, it will get suppressed to 0. If you look at this on the gradient magnitude, like as you go from layers, input to output, in the top layer, it probably there is at least some loss. Okay, so the way to read the left graph is basically the bottom x-axis is the layers. Try to, So the bottom x-axis is the layers. That means output layer is near to the 20. Input layer is this one, and the left one reads from 10 to the power 0 to 10 to the power minus 16. That's the gradient magnitude. So if you look at in the input layers, the closer to input layers, they have 10 to the minus 6 level of gradient. That means there is no gradient flowing back. Those weights will never change, right? And so that's how you basically try to improve on stuff, yes. And you can use specifically like ReLU plus timing initialization you can use that will get also improved. ReLU itself can also help you improve. But yes, ReLU, if you see, it immediately drops, right? So because everything beyond negative is 0, so for it drops very quickly. So with ReLU, you have to use all those uh, other things as well. Now, this is a chart for regularization. So if you look at the left hand side and the right hand side, left hand side is basically the training loss. Basically, you're trying to find W. The right hand side is validation loss. And I told you the moment validation loss starts increasing, we have an issue. But for these two graphs, there is nothing. Uh, but here, what we want to say is okay. So the training can be more stable. Like there is no be increase and decrease won't be there. Uh, there is no overfitting as such. But if you do L2 regularization, for example, training loss reduces slow, but at least validation loss also reduces slow. Yeah. So it is a much more smoother curve in that sense. Yes. And if you look at overfitting, well, validation training loss increases. L2 regularization also increases validation training loss after some time, but at least it reduces to a much deeper point. So that helps. But based on data set, actually it improves. But you can run it again and again and to see those curves. Yes. This is another curve to show like the batch normalization and without batch normalization, what happens. If you do look at this might not be visible to you, but if you look at this particular graph, there are a bunch of lines near to the 0 and 0.5. what is happening is the frequency of all these activations lies within that particular range. If you use batch normalization, the basically the values are well spread out. That is what you would want after, yeah, so that every part of the layer learns. And that's right there. Fine. Then we have this is for the fourth one. So if you have gradient flow, this is like the 5 layer and this is 10 layer. What exactly happens? Uh, and this is after, let's say, 20 layers and like 50 layers. The more you increase the number of layers, basically the gradient basically reduces. That all it says. Yeah. Uh, Next goes, yes. Okay, so these are all the loss functions that we discussed: MSC, MAE, Huber loss, and there's a log cosine also. So, oh, log cos h, sorry. So this is again like MSC will have very smooth, MAE and Huber we discussed. Uh, Penalties don't appear for outliers in like MAE and Huber. Much better. Huber is just a combination of MSC and MAE. Yeah. And multi-level, let me see. Okay. Fine. So multi-label again, what we do is I told you like we calculate loss across different labels. So here we can calculate per label accuracy, yeah, and then we can calculate mean. So instead of one example having just one label, many classes here each unit itself can be multi-label. That means many number of labels are associated with one particular example. Yeah. This is another example you can please try. This basically says how is the label distributed across during training and during testing. And if you have multi-label accuracy, you would basically report the mean of it. Yes. And how good are you with product prediction probability of all those given the label indexes 1, 2, 3, and 4. Let me see. Multitask. Dropout. Okay. Multitask also, you please give it a try. Then, okay. So, this is dropouts. Dropout will make more sense probably. This example. Okay. So there will be another code in the next class. I will show you dropout a little bit more animated. Fine. Okay, so these two cover basically all of the things that we had discussed till chapter 4. Fine. In summary, what we discussed is like what are neural networks? How do you train them? What are the various different words that will come across? Optimization, Adam, per parameter learning, momentum. Yes. All these terms come up, then regulations such as we do dropout, then we do for stopping overfitting data augmentation. Uh, there is also always stopping. All these are things that has to come. Then there is learning rate decay, and all those variances are there to make sure the learning rate either improves faster or we can start with bigger numbers and then slow it towards the end and so on and so forth. Yeah. So I hope that gives a bunch of ideas on like where the neural network research has gone through. And I will share the slide. I did not update last week, my bad. I will update it today, and so that you can go through and run all these slides and have an idea. And then in the next class, we will discuss a bit about CNN. So one of the advanced algorithms a little bit more in detail, where we can look at all this dropouts and all this stuff more, how do I say, more with figures. Yeah? So that will help you in understanding a little bit more better. Yeah? We'll also look at spatial dropouts, channel dropouts. Yes. Okay. That's it for today. If there are any questions. Again, just giving and repeating, maybe all of the topics might not be super essential, like super critical to you right now, but at least you should be able to relate them when you read papers. That's the entire motivation for this. Okay. If there are any questions, please drop. Yeah. And the next class will be on Friday, not Wednesday. Wednesday is a holiday. And we'll have only, I think, maximum one more class on machine learning itself, and then we'll move to practicals on materials and machine learning. We'll try to make sure discussions are there as much as possible on materials paper also. And for the final presentation of all the credit taking projects, do I announce that process name?
Uh, no, sorry, precisely what?
Oh, the presentations of the things.
Yes, we can have presentations. Yes.
Yes, yes. So all the students who are taking like basically the credit for this particular courses, we will expect one instead of submitting a YouTube video, you can do a live presentation of your entire project
Yeah,
at
it should
towards the
be.
end.
We will have live presentations
Yes, yes, yes.
rather than videos.
Yeah.
Yeah. So next week, so you will have one more lecture on these for 1 hour.
Yes, on Friday. Yeah,
Yes.
yeah.
So next week
And yeah,
onwards, we'll start with examples on materials, and
yes,
I'll start from the simplest models first,
yeah,
and then maybe slowly go over to more complex things, which will
yeah.
be actually relevant to the projects that they are doing.
Yes. And also, if you like to discuss one of the papers that you are going through, we can take that up also. Like, as
Yes.
in, that can be a class where we discuss that paper, what they're doing, why they're doing, what features they're taking, and all. So, we can do that also. Like, please feel free to email. And I think we have mailed, talked with all the credit students that you should start a chain with us. So, please do. Yeah,
Yes. So although it's an online class, but
yeah,
the number of credit students are is relatively small, and you don't have to sit quiet there. Just treat it like a normal class and interact, write emails.
yeah,
We want it to be, particularly now onwards, we want it to be more interactive.
yeah. Okay, so like only this Friday, after that, we will be having, hopefully, we will be also sharing screen and showing us for the next of the classes. Yes. We'll
Yes,
expect that you to be with us. Yeah.
yes.
Yeah. Okay. Okay. Fine.
Okay,
All. Yeah.
we'll meet on
Yeah.
Friday.
Yes. Bye all. Yeah.